Okay. Okay, welcome everybody to this Auckland Structural Group presentation from Associate Professor Hamoud Al-Washali. He's going to present on a very interesting concept of concrete frames reinforced with CLT walls. Hamoud has come all the way from Okayama in Japan, so I'll leave Hamoud to talk about this concept.
Hello everyone, I'm glad to be here. So before I start, I'll just give a brief biography, or I'll talk a little bit about myself. Originated from Yemen. I finished my bachelor degree in Jordan, and then from 2013 I've been in Japan. So I've been in Japan for around 12 years. So I finished my master's, PhD, and then worked in Tohoku University, and then moved as an associate professor to Okayama University. So what do? I do structural design, analysis, and especially seismic design, because as you know, Japan, similar to New Zealand, the earthquakes are every 5 years there is a big earthquake. And my topic is actually reinforced concrete, and in my PhD I did masonry infill. Recently I started to do more about timber CLT wall. I'm not sure if I've known that in Japan, and recently is focusing a lot about SDGs and CO2. It's not only Japan, I think the whole world. And CLT is getting a lot of attention, and not only CLT, timber design. So a lot of my work was doing earthquake damage surveys. So when I was in Tohoku University, if you know where Tohoku University is, the place where actually nearby the big tsunami in 2011, which happens, the big earthquake there. So after that, there was a lot of damaged buildings, and I was lucky I wasn't at that moment in the city. But after that, when I came back to finish my master's, I visited many buildings and I did a lot of damage surveys there. This is one of my experiments I have done, and this is not related to, this is the damage survey. Actually, this building is one of the buildings in Tohoku University, inside the campus, which was severely damaged. It was the civil engineering building. So the civil engineering building and damaged, it was a big story there. And this is one of my tests previously. I do some analysis. So most of my tests is, most of my work is both investigation on site, experiments, and some analysis. Other activities I'm actually doing, Japan now is trying to be more international and to collaborate with more international universities. So in my university, I joined something called the new research center called Green Innovation Center, and they are concentrated more how to make international connections related to green buildings or timber buildings. I started to make this something called global seminar. So the first year when I joined that university, we started only online, and then I invited several people, but only online. And then next year it was hybrid. I invited two professors, one from UK and one from Turkey. But last year I had the chance to invite many professors, many researchers from Sweden, New Zealand, Germany, and Australia. I think you'll find Gary here. And this is also Alex here. And this year also, this was last year, and this year also I'm trying to prepare something similar to that. Okay, I'll go to the topic. So my original field is reinforced concrete. When I visited many of the buildings there, and this is one of the buildings damaged after 2011 earthquake in Sendai city, near my university. And RC walls in Japan, a lot of them are structural, but also non-structural walls are used. So this damage, you can see them are, sometimes you have seen them in non-structural RC walls. So even for walls that are not working as a structural elements, they use reinforced concrete walls. This building, if you see the beams are okay, columns were okay. I didn't show the columns here, but they were okay. But people, because of this damage and reinforced concrete walls, doesn't want to live there anymore. So they demolish this building, and they build a new one because people doesn't want to live there. This is another building, and you see this is not a wall, not a column. This is actually non-structural RC wall. What I want to say is RC walls are strong, they're effective, but if they are damaged, it's not easy to repair. And I think most of you knows that. It's the epoxy injection and everything is very difficult, and if it have a damage like this, it's not easy. So one idea to think about it is, okay, why don't we replace this RC walls with something more ductile? So we don't have any more RC walls, we have CLT walls. So CLT, I'm not going to talk a lot about CLT. I think you already know that. It's cross-laminated timber. It's light. And here I say it's easy to repair. Why I'm thinking it's easy to repair, even if it's damaged, you can remove the whole wall easily, replace it with a new wall, and that's all. It doesn't take much time like reinforced concrete. The other thing, it's high shear strength. So when I first studied CLT like 3-4 years ago, I was surprised that the shear strength of CLT is almost similar to reinforced concrete, 3 megapascal, which is high. So even if we replace it, reinforced concrete, the strength will be almost like reinforced concrete wall, which is really good. So this is the main motivation, that we have a lot of RC walls, we can replace them. We put CLT walls, and we have a building, something like this. And of course, CO2 is a big topic now, either here in New Zealand or in Japan. But actually, there are several problems with that idea. You have many failure modes. It's like, how will the failure mode happen? It can happen in the punching shear here, or like a rocking behavior of the whole system. Another one is shear failure in the columns. And one of those topics is that we have kind of a compression strut here, and the CLT fails in the compression strut here. So what I'm going to talk about here is I'm going to talk about how to evaluate this kind of failure. This is a kind of a new topic in Japan. The last 8-9 years, several professors started to do the same thing, or not the same thing, on the same topic. So nowadays, I'm collecting a database. There are almost around 30 specimens from different professors. We are doing different failures on this topic. So what is compression strut? And if you see an FEM analysis, if you push it like here, most of the stress on the wall will be concentrated here. Maybe some of you have worked with RC walls. The same thing have a compression strut. I'm sorry, I'm not sure why it is jumping. Just a minute. And if we try to evaluate the strength, the easiest way is, okay, let's have an equivalent strut width. If we try to get that strut width and make it equivalent, because what does equivalent mean? There is stress variation between this. So if I try to get something like an average for that, and try to get this width and this angle, and multiply it by the compression strength, I can evaluate the strength about it. I'm going to talk about this in the next slides. But what I want to say here is I'm trying to evaluate how much is this width, how much is this angle for a CLT. And the whole story now will be about that and how to evaluate that. Okay, so I've done this test last year and for 2 years. The first year, one specimen, the other year, another specimen. I had, until now, 2 specimens. Both of them are identical. It's a 3rd scale specimen. Height is 1 meter, and the span is about 1.7 meters. So what is different between those 2 specimens? One, I put something called here shear keys, up and down. And the other one, there is no shear keys, just put it there, and I put like a gap around it, just a 4 millimeters gap, and filled that gap with epoxy. The other one is also, there is also a gap but there is also shear keys. I thought shear keys will be good to transfer the shear strength, not only on the corners here, but also here and here. It will be well distributed, and that's why I thought about those two specimens. And I tried to compare how it will work. The CLT I used is something called grade MX60, which means the MOE is 6,000 or 6,000 megapascal. Japanese cedar, or if you know timber in Japan, it's called sugi. The thickness of this wall is very thin. It's only 6 centimeters. So the columns are 200. The wall is only around a third of the thickness of the column. So the loading setup is, it is a horizontal jack here, which I push and pull using it. Static cyclic loading. And also there is a vertical jack here, putting a stress about, I didn't write it here, but it's about 0.2 of the compression strength of concrete. So around 200 kilonewtons. This one 400 kilonewton. Each column 200 kilonewton. And there is a pin connection here. So what I'm assuming that the 400 kilonewton here, it goes 200 here and 200 here. That's the ideal assumption. And the horizontal jacks pushes here. And I pushed until story drift of 3.2%. What kind of concrete strength? Concrete strength is about 21 megapascal. This is the nominal concrete strength. And I used the steel in the columns was D16, which is diameter 16, and SD 345. It means minimal yield strength, nominal yield strength of 345. For CLT, I used MX60, which means the grade is 60. But what I tried to do here is, as you know, CLT, because of its timber, each direction have a different compressive strength. It's not like concrete. Concrete, it's easier. You have one Young modulus, one concrete strength, and that's all. For CLT, you have the parallel to the grain is strong, and the strong, or they call it sometimes the major axis. And perpendicular to the grain, this one is a little bit weaker, which they call it the minor axis. So the major axis was around 21 megapascal. The minor axis was around 12 megapascal. And because I'm thinking about compression strut on an angle, so I thought, let's try to do the compression strut on different angles. So I tried to do it on different angles of the CLT, to cut the CLT in different angles and do the compression strength. What I found out is that it's actually the weaker direction of CLT is not the perpendicular to the grain. It's actually at 45, or it's between 60 and 45 degrees. It's much more weaker than the perpendicular of the grain. So the strut direction is actually the weaker direction. And for me, that was new because I am not used to work with CLT. I was always thinking that the perpendicular to the grain is the weakest. Anyway, so as I said, we want to calculate the strut. Let's think about, this is the strut, if you think about one strut. And I need to know the strain, or stress and strain at each location. So what I tried to do is, okay, let's divide this into small boxes and attach a strain gauge here, triaxial strain gauge. And assume this triaxial strain gauge represents the whole box here. The same thing here. This one represents the whole box here, and so on. So I divided it into 35 boxes and attached triaxial strain gauges to get the strain at each location, and based on that, I get the average and then try to estimate the strut width. So how does the specimen looks? It looks like this. With the help of students, I could finish that. It's a lot of work. So this one to attach the strain gauges, me and 3 of the students, it took us the whole day to attach it carefully and one by one and label that. Because it's 35 triaxials, but it means each one have 3 strain gauges. So it's more than 105 strain gauges only on the panel. Okay, so I'll go to the experimental results. So first I'll show you the one without the shear keys. So if you see here, at around 0.8%, the column yielded, and after that, at around 1%, it reaches almost maximum strength. After that, it goes almost straight. The maximum was around 2.7% story drift, around 350 kilonewtons. This is both RC and CLT. And RC frame alone is only around 150. So CLT is carrying around 200 kilonewtons. More than half of the strength is carried by the CLT walls here. This one, at the final at 3.2, which is very large drift, it actually failed out of plane. It went like this, outside. But when I released the load, it returned back. But we stopped loading at that point, and we considered that it's already failed. And if you see here, there is a lot of gaps here and here. We are pushing in this direction. So this is attached because the strut is in this way. And here's the gaps between those. So this is without shear keys. And then I thought, okay, if I attach the shear keys, it will be much more better. And so I did the shear keys. The shear keys is just those here. It's a concrete shear keys. So when I casted the beams, I cast it all together. It's concrete. And honestly, didn't improve much the strength. The maximum strength was almost identical. This dotted line is the one with no shear keys. And the dark line here, the black dark line here, is the one with shear keys. So the one with shear keys is a little bit stiffer at the beginning, the initial stiffness, but the maximum strength is almost similar to the previous one. If you see, the previous one was around 350. This one was around 336. But this one, around 1.6%, it starts to have this kind of vertical cracks around the shear keys. So there was some kind of concentration of stress around the shear keys. And this splits. It's one panel, but the panel splits into kind of 3 panels. To show you what happened at a very large angle, so it looks like this, and then we pushed, it moved like this. I don't have the time to show you the whole videos of both specimens. I'll show you a video of one of the specimens here. Just a minute. Okay, so this is going, this is showing how we are going in a small, now still loading at small angles, here and here. You cannot see it moving yet, but it will be moving soon when the story drift becomes larger. You can see it now coming right and left. And at around 1.6%, the next cycle, you can see the vertical cracks here start to split. And then we pushed all the way until 3.6%. Okay, so there is a lot of analysis we have done. I don't want to go deep, but I'll give you the main points what we have done. So at each location, we tried to analyze we have 3 strain gauges, and based on that, we tried to calculate the principal strain. And the E minimum, which means the compressive principal strain at each location. So if we are pushing like this, this was the principal strain at each location. This one's here, if you see, it didn't have much. And then we found out that when we attach the strain gauges, there is between the CLT and CLT, there is between the laminas, there is a small, not a gap. The there's a line between the laminar and the laminar with the CLT, and the strain gauges were there. So we are thinking in that location it was not captured well, but in other places it was well captured. This is with shear keys, and this is without shear keys. You can see if we push it here, a lot of the stress in the corners, and also in the corners here. In the middle, the distribution becomes a little bit larger. And based on each one, we also calculate the angle of the principal strain. Just more circle idea. It's not that difficult. The equation looks difficult here, but it's just more equations and try to calculate which direction is the principal stress. And then based on that, we got, so just all of this, each one of those, we tried to calculate, if we take the average of those and try to calculate which angle this will have. And because some of them, they have less strain and some of them have larger strain, we can calculate first based on the strain value averaged with the angle. So if it's a larger place, have a larger strain, it affects more. If it's a less strain, it doesn't affect more. And then we calculated how much is the angle of that strut. So without shear keys is this one. With shear keys is this one. There is, at the beginning, it starts a little bit higher direction, and then the angle goes, this angle goes down, down, and down. If you, these two angles, if you think about it, it's almost the diagonal angle of the RC frame. So I'll go back one. So this angle actually, if we just pull an angle from this diagonal to this diagonal, it's around 38. So what we are having here, it's around 38. But the one with shear keys is a little bit higher. It's going a little bit up. I think that affects because of the shear keys. And the same thing we did with the strut. So we have a lot of strain gauges here. And then we tried to take the average of those strain gauges. First, we divide it into 9 stripes. This red ones, 1, 2, 3, until we get to 9. And then each stripe, we can get how much is the average of the strain gauges in each stripe. And then we get the average of the strut width in that location. An easier way, it's like we can get the strut width here, and strut width here, based on the value of the strain gauge and average of each stripe. And then we can get the average of the whole thing here. This idea is actually not my idea. It was used in another research for masonry infill, and for another professor working with us, and we used the same concept. So what I want to say is we got the equivalent compression strut width. So how much equivalent strut width? At the beginning, the strut width is bigger, but when we push more, it gets lesser and lesser, but higher strains. But it's at the maximum strength, which is around 1.6%, it's around 700 millimeters. That's the strut width. To visualize it, to make it easier to visualize, it looks like this. So this angle for the no shear keys is around 36, and the strut width at the maximum one was around 616. And for the other one, for the shear keys, it's a little bit up. So a little bit bigger, this angle, comparing to this one. But the strut width is a little bit bigger, but also comparable. So the shear keys didn't affect much the strut width, maybe a little bit the angle. So why did we calculate all of this? So we calculate the strut width, strut angle, so then what? An easy thing to think about it is strut width multiplied by the thickness of the wall, multiplied by the compressive strength of CLT at that angle, multiplied by cosine theta of this angle, which is you want to get the horizontal component, you can get how much the CLT is carrying at each step. If we know this strut width, even before the experiments, we can even calculate it for a new walls or new buildings. And in a similar idea, we have this brace. We can represent it with this brace element, like an axial spring. And if we want to design a building, we actually need something to represent it like this. So RC frame is just represented by normal rotational springs and shear springs. And CLT walls are represented by one axial spring. So to make this axial spring, we had to think about what kind of model, how to model that one. We assumed it as a bilinear model. So it goes until the maximum strength, which we can calculate using the strut width. And then it goes almost straight. Of course, at some point, there will be degradation. But in this model, we don't think about degradation. We think about it's going all the way, which is a topic that we need to improve in the future. So using this model, and then we try to evaluate how much strength and how much it represents the experiments. So this blue line is the model. And this gray one is the experiment. So if you see the initial stiffness kind of well represented, the maximum strength kind of well represented. After that, there is degradation or the splitting of the walls, which is not represented in this model. But usually for design, we need it until this point. How much is CLT and RC frame is actually this green one, not green one, this yellow one is the bilinear CLT, and this green one is the RC. If you combine both of them, it becomes this blue line. Easier. And the same thing for the one with the shear keys. The one with the shear keys, there is a little bit difference here. The model slightly overestimates it by around 5% or 6%, but we can get we can capture the overall behavior of the tests. Okay, so until now it's maximum strength and analytical model. So stage 2 is like, how about repairability? So when I started my presentation today, I was saying it's better for repairable and we can remove it and put it easily and that all talk. So I said, okay, so can we repair it easily? So what I did, this is a stage 1, what I showed you before. I removed the whole CLT wall and then tested only the RC frame, even if it's already damaged. And then again, I put a new CLT wall inside it and then tested again to see how is it working. So I removed the CLT wall, and then this is when I removed it, and then tested only the RC frame before I put the CLT, after it was damaged. So by using analysis model, it should be going like this, the blue line, but because this is already damaged from the RC wall, because it's already damaged and have some cracks, so the initial stiffness degraded, but the maximum strength, since it depends on the repetitiveness, still doesn't change much. And then we thought that's okay. We haven't repaired the RC frame. And then we put a new CLT wall and tested again. So the blue, the original one is the black one, and the repaired specimen is this one. If you see, there is slight difference, not slight, kind of some difference here. And this difference is actually not from the CLT. We haven't repaired the RC frame. So the RC frame stiffness is reduced, and that's why there is this difference. If we repaired the RC frame using epoxy or anything, I think we will have almost identical thing. The nicest thing about this, when we remove the CLT wall and put the other CLT wall, it's only me and my students. So it doesn't need that difficult work to cast concrete or other things. Like remove it, CLT wall are not that heavy. Maybe this is an experiment, but even so, it's not that heavy. Two people can remove it kind of easily. And then when we put the other one, it's not that difficult. And then fill the epoxy around it, and then we test it. So we think that it's good in repairing. So if you think about only CLT walls, remove this RC frame. And this is the first specimen, and this is the second specimen. If we think about CLT walls, so I subtract the RC frame curve. The one I got it, this one, if I subtract this one from this behavior, and then I can get how much is the first specimen, the second specimen. Both of them are almost identical. One thing is energy dissipation. Energy dissipation for both of the specimens we calculated using equivalent viscous damping, calculating the energy inside each loop, and compare it to the potential energy. I think maybe you already seen that concept in some places. And this is the original specimen, the blue one, the black one, and that's the other one. If you see here, it starts with 3%, and then it goes up to 10%. So usually RC walls, it's a little bit higher than 3%, usually 5% or so. I think CLT, the energy dissipation of CLT is less than RC walls because it doesn't have much cracks. But it's also, I think the energy dissipation was well. So this will be the conclusion of what I have done. It's like CLT panels acted as effective shear walls using the diagonal strut action. If you think about RC frames, it boosts the strength about 2.2 times. Without shear keys, it failed in out of plane. But with shear keys, out of plane stability was better. But actually, we have concentrated stress around the shear keys, which had those vertical cracks. So it's good and not good. The simple macro model, which I represented like a brace model, it's easy to put it, and it can represent the experimental results until peak strength. After peak strength, there is degradation, which we need to account for. That will be my conclusion. So I have still 2 more slides. So what's next? So I haven't said in the previous one that actually the hinges were in the columns. So we designed the beam as a strong beam, weak column. So what I want to do this year, when I return back here, after I return back to New Zealand, then after 2 days, I'll go to cast those specimens. What I will do will be, we'll have a failure in the beams, not in the columns. So the previous ones, the hinge was here, because we were thinking about older buildings. Now I'm thinking about new buildings. New buildings, the failure will be in the beam, so the hinges will be designed to fail. That's I'm going to do in October and November. If you happen to be in Japan in that time, I can show you the specimens. We have also a new project which we started with between Tohoku University, Okayama University, and New Zealand University of Canterbury. And we are thinking about modular seismic retrofit system. The idea in simple ways, in my previous one, we just put the CLT here. We are thinking if we put something called PXEM, which is phase exchange cellular material. It's kind of a new material developed in Purdue University in the States. It can absorb more energy. So it acts as a deformation buffer. It will reduce the member damage. It will also absorb a lot of energy. And we are trying to test that. This year will be like a planning, and next year will be tests in Japan and also test New Zealand and Canterbury University. That's all for my presentation, and that's Okayama University. A nice CLT building there. If you happen to come to Okayama University, I can show you around that building. Please feel free to contact me. Thank you.